Good morning. All right, we made it through chapter 1. We are moving on into chapter 2. This is where we're going to start hitting the real physics. So it looks like in chapter 2, we're going to be looking at a topic called kinematics. Now, kinematics just has to do with motion, describing motion. So kinematics is keeping track of things like velocities and accelerations. And yeah, there's your automobile going some number of meters per second. So here are the individual sections within the chapter. Now, when we're measuring velocities and displacements, distances that objects have traveled, what we have to ask ourselves is relative to which reference frame. So we have to think just a little bit about a reference frame. So for example, let's say that this person is walking through the train car and the other passengers look up and they go, how fast is that person walking? Oh, they're walking 3 meters a second. You know, that's a pretty good clip. And so maybe 2 meters a second. So this person's walking at 2 meters per second, but that's measured by the people on the train. How fast is that person moving if someone outside the train measures them? So maybe the train's going 30 meters per second, and so for the person outside, we can just use velocity addition. The train is moving at 30 meters per second, and the person within the train is moving an additional 2 meters per second. So that's going to add up to be 32. Now, why is this such a big deal about reference frames? Well, it turns out everything we do in physics, all of the formulas, all of the quantities we're going to define will work, everything that we talk about, as long as we're in what's called an inertial reference frame. If we're in a constantly moving reference, like on the train, then, you know, if someone was on the train throwing a ball up in the air, playing catch in the aisles, it feels the very same as if they're out on the ground. If you're in an airplane going, 500-600 miles an hour, you can go out in the aisle and just walk back and forth, and it just feels like you're back down on the ground, right? And so all of those constantly moving objects represent inertial reference frames. All right, so what we want to start off with in doing these measurements is we want to be making these measurements in an inertial frame. And so we want to make a distinction between distance and displacement. So what they're saying here is, let's imagine that someone walks a distance of 70 meters, but then they turn around and they come back 30 meters. Now, the distance that they walked, we could say, was 70 plus 30. They walked a total of 100 meters, right? But the displacement is keeping track of how far are they compared with where they started out. So displacements are not concerned about the path between those 2 points. Displacements are just concerned with where did you start, where did you finish. So that distance represents a displacement. Now, the distance of distance includes, stopping, turning, going back for a ways, then going forward, all of those variations that took place. So displacements can be written this way. So we want to start developing some mathematical formulas, some math to describe what's going on. So what we could do is we could say that a displacement could be written, one way to write a displacement would be to write delta x. So delta x would represent where the person finally ended up compared with where the person started out. Now, what we're going to need to do is set up some type of a coordinate system. So we have to decide, where is the x-axis, where is the y-axis, how are we going to measure these things out? Well, the motion in chapter 2 is only along one path. And so all we need is, mathematically, we'll just say, let's imagine there's an x-axis with a bunch of distances marked out on the x-axis. Now, they're saying that, there's an origin right here, and that the person let's see, what did happen here? This person started out at the 10-meter mark and then walked out to the 30-meter mark. How much of a displacement was that? And we'd say, well, in this coordinate system, we could use the numbers 30 and subtract 10. That's where we ended up minus where we started. And we would say that x2 represents a displacement of plus 20 meters relative to x1. So we've traveled 20 meters. And that displacement can be written as an x2 minus x1. Now, what happens if this person walks, there we go. So what happens if the arrow goes in the opposite direction? Well, it's the same distance that the person traveled, but it's in the opposite direction. Now, we want some way mathematically to keep track of plus and minus signs. And what you're going to find out as we go through physics is that sometimes we can get the formulas to keep track of the plus and minuses for us, or sometimes we have to use a little of our own understanding of the problem to determine where the plus and minus signs go. In this example, using this coordinate system, going from x1 to x2 in the left example, represents a displacement of positive 20 meters. Going from 30 back to 10, see how the x1 is the starting point and the x2 is the ending point? That represents a displacement of negative 20. So we actually can keep track of plus and minus. Now, you know, if I walk over here in this direction and then I turn around and walk back over here, there's nothing inherently positive or negative about either of those directions. But what we've done is we've put a coordinate system in, and now we're using everything relative to that coordinate system. Okay? And that's why we're going to designate one as 20 meters and one as negative 20 meters. Now, we can move on from displacement and start talking about velocities. So how fast are things moving? Now, an average speed or an average velocity, we can say is the distance traveled, and notice I highlighted distance, divided by the time elapsed. So in that earlier example that we looked at, we said that the total distance that the person had walked was 100 meters divided by 20 seconds. So we would say, you know, the average value would come from taking the 100, dividing by 20. That gives us a value of 5. Actually, they should have written this as 5.0, right? So this should be, oh, maybe I wrote that. This should be 5.0, and then meters per second. So we're going to say that the person's average speed was 5.0 meters per second. Now, what happens when we move on to the average velocity? So I think I said velocity up here too. Textbooks tend to be really careful about this. So they say speeds are just distance between divided by time, whereas velocities are displacements. And I guess I should follow that convention. It is pretty well established. So in terms of, well, how far did the person get? Well, they only got to be a distance of 40 meters and it took them 20 seconds. So on average, they were only moving along at 2 meters per second, even though on average, you know, the average speed was 5 meters per second, but the average displacement was only 2. If they had walked all the way, and that's just for one direction. So I guess if they have, we got to go back and take a look at this now, huh? Yeah, so it's going all the way back to this example, not the picture right. This one, not this one. Okay. All right, so now let's take a look. Here's an example that we're supposed to go through and do the calculations on. So let's try this. It says that we're looking to calculate a runner's average velocity. It says that the position of a runner as a function of time is going to be plotted as in terms of moving along an x-axis of a coordinate system that we've decided to use. So we've decided to set up this coordinate system, and within our coordinate system, the runner is going from the 50-meter mark to the 30-meter mark, and that all takes place during 3 seconds. That's a pretty short time interval, it seems, but that's what's happening here. The runner's position changes from the 50-meter mark to the 30.5. So they got down to tenths of a meter there. What was the runner's average velocity? So we can follow the reasoning that we talked about. So to represent an average velocity, now that's a V. I apologize if that little bit of my V hangs over here. That is a V, not an R. That's an average velocity is equal to delta x over delta t, where delta x represents the difference between two position measurements, and the delta t represents the difference between two time measurements. So now, using the deltas or not using the deltas, we can use the deltas or don't use the delta. It's really for our benefit. So if conceptually it makes more sense to be using the deltas than I think it does here, I'm going to go ahead and use deltas. If you want to think of t all by itself as a time interval, that works too. So anyway, I think the deltas are useful to get started with here. So let's just put all the information in. We started at 0 seconds and at the 50-meter mark. So I'm putting in t1 and x1. And then I'm going to put in t2 is at 3 seconds, and x2 is at 30.5 meters. So what that tells us is that delta x in our coordinate system is negative 19.5 meters. And that's going to get divided by the time interval, t2 minus t1. And so displacement over time interval works out to be 6.50 meters per second. And I got the 3 significant figures in there on my answer. So this is going to be our average velocity. Now, average velocity is saying we don't know if they ran at a constant velocity or not. If they were running at a constant velocity, then that 6.5 represents the velocity during the entire time. Otherwise, no. It could have been varying. Here's another average velocity example. It says here we have a cyclist traveling, and the cyclist is going to travel for 2.5 hours, and her average velocity is going to be 18 kilometers per hour. How far will the cyclist travel? So, you know, the cyclist is thinking, hey, I can average, is that a pretty good speed? It's a relatively, level road, and I can maintain kind of an average of 18 kilometers per hour. So let's, on this example too, this is the average velocity, delta x over delta t. And so I can solve for delta x. Delta x is going to be equal to the average velocity, and I've drawn that line over the top of the V, a bar over the top, to represent average. And then the time that the cyclist is going to travel is 2.5 hours, and she figures she can maintain 18 kilometers per hour. So the displacement we're expecting is 45 kilometers total. So, and there is the bicycle. Did we get we got the right direction on? Oh, I see. Okay, never mind. So in this case, here is the coordinate system. Here is x1. Here is x2. In this case, we just solved for delta x directly. We didn't have to work in terms of individual x2s and x1s, and the delta t was given. So we didn't have to work in terms of individual t2 and t1s. Okay, but we could have. So just showing the connection between this and the problem before. So those are the average velocities. So, working through these examples, this is going to give you an idea of what the homework problems look like and what some of the midterm problems look like. They're going to get a little more involved here. Here is a speedometer, and it says that what we're looking for is an instantaneous velocity now, rather than an average. Now, I always thought of a speedometer as giving us an instantaneous velocity. What this is saying, and I'm not sure why, it says that a speedometer would ideally give an instantaneous velocity, but in fact it measures average velocity, but over a short time interval. So this is going to depend on how the speedometer is built. If the speedometer has a cable in it that spins around and is connected right to the mechanics of the wheel, then as the wheel spins, that cable will rotate and the speedometer is gonna. So I'm not sure the workings of a modern day speedometer, but maybe it is measured. Distances are measured over very short intervals to give something very close. Now the part that we're interested in here is not so much the speedometer, is that we can get an instantaneous velocity by measuring over shorter and shorter time intervals. So rather than waiting, 10 minutes between measuring how far we've traveled, what if, every second we measured how far we traveled? Or what if every millisecond or every microsecond? Well, in the limit where we start measuring those time intervals over shorter and shorter period of time, the delta x's are going to get smaller too. So as the delta t's get smaller, the delta x's will get smaller, and in the limit of that, we can bring that back to our friends from calculus, dx divided by dt. Now in calculus, we talk about this as being the first time derivative of x, and that is one way to think about this. But we can also think about this as a ratio of a short displacement divided by a short interval of time. A very, very tiny displacement divided by a very, very tiny time interval. All right, so here is a graph of an object's position versus time. Now, the textbook is going to be using the word particle for any kind of an object. They're treating it as if the object is fairly compact. Sometimes it's not. Sometimes it's a car traveling down the freeway. But I'm going to tend to use the word object instead. So let's say that we have some kind of an object, and here is x as a function of t. And so what we've done is we plotted a lot of data. So what we did is we found out, as a function of time, where is it located? Once we've collected a bunch of data as to where the object was for every instant in time, we can plot that. So we've got this nice red curve going on. And then what we can do is we can start doing average velocities. Let's say we pick a point here and a point here. Well, that represents a certain time, t1, when the object was located at x1. And this other point represents, on our graph, represents a time 2, and when the object was located at position 2. So that's kind of the same stuff that we saw in those earlier formulas. So now what it's saying is, well, I could then say delta x is x2 minus x1, and delta t is t2 minus x, and then I could take the ratio of delta x divided by delta t. That would give me an average velocity. So the average velocity on our graph would be rise over run, and that would represent this straight line. So the slope of that line is our average velocity. That's a graphical representation of what the velocity would be. Well, if you look at the graph, you can say, okay, fine, this is giving me an average velocity, but notice here, I wasn't going as fast as the average, and then in the middle part, I was going about the average speed, and then I picked up faster than average. So in reality, it would be nice to have all the information about how the velocity varied. Now, the information's there, because what I would have to do then is just look at the slope of the line if I look at the slope of the line at each one of those locations, the slope at any point along that line would give us the instantaneous velocity. So I collect a bunch of data, we plot it all on an x versus t graph, and then we can see what the slopes are like. Now, what they've done here, I think, is what they're doing is they're looking at shorter and shorter time intervals. Now, eventually, when we get down to those shortest time intervals, then it becomes dx divided by dt, and that ratio is the instantaneous velocity. Okay. So let's try an example here. It says that we're actually going to be looking at accelerations now. We're going to move on and take a look at an average acceleration. Now, an average acceleration is going to be a difference of velocity divided by the time that has elapsed. And so what we can do then is, here's a car. It's accelerating along a road from rest to 90 kilometers per hour, and that takes 5 seconds. So this time the velocity is not constant, and the car is picking up speed. And the acceleration that we're given here is 5 meters per second per second. Okay, so when t is equal to 0, the velocity is 0, it's starting from rest. But after 1 second goes by, with an average acceleration of 5 meters per second, we're going to be traveling 5 meters per second. After 2 seconds, we're going 10 meters per second, and then after 5 seconds, we're going 25 meters per second. Now, I don't think they have the distances worked out here right, so the distances don't seem to match up. But anyway, let's take a look at the drawings they've given us, and then we'll get to work on solving this. I just want to point out that 90 kilometers per hour is not in standard units. Those kilometers have got to get converted to meters, and the hours have got to get converted to seconds. So one way to do that is to take the 90 kilometers and write that as 90,000 meters, and take the hour and write the hour as 3,600 seconds. So if I take 90,000 divided by 3,600, I get 25. So the speed they've given us, the 25 kilometers per hour, is 25 meters per second. So that's what we're going to use, is that 25 meters per second. Now notice, the 25 meters per second, we went from rest to 25 meters per second, and that happened in 5 seconds. And that's where they're saying the average acceleration then is 5 meters per second each second. Okay, let's see how this works in a bit more detail. So the average acceleration, so this is actually picking up speed, is going to be delta v divided by delta t. So v2 minus v1 divided by t2 minus t1. That's a difference in velocity divided by a time interval. Now they told us that the starting velocity was 0. It started out at rest, and then the final velocity, the later velocity, we calculated out to be 25 meters per second. So that's what we're looking at. Now, if we put the numbers in for that, and I guess the time, we got to get the times figured out here. We started out, we're going to call the starting time 0 seconds, that's easy. And then we can call the later time 5 seconds. So whenever we can, put a 0 in, why not? And we can, there's nothing preventing us from putting in 0 for the starting time, and the starting velocity was 0, we were told that number. So that's going to be an increase from 0 to 25, and it's happening during a time interval of 5 seconds. Now, this is an average velocity, an average acceleration, sorry, of 5.0 meters per second squared. Now, if it is constant, if that car is constantly increasing its speed at that rate, it's going to go from 0 meters per second to 5 to 10 to 15 to 20 to 25. So here we've done times of 0, 1, 2, we left out 3 and 4, and we jumped ahead to 5. Those are the pictures, the values that they had on those earlier pictures. Okay, so we're into acceleration now. So we've looked at displacement, we've looked at velocities, and now we are getting into accelerations. So here's a conceptual question about velocity and acceleration. If the velocity of an object is 0, does that mean the acceleration is 0? Now, velocity and acceleration are two different quantities. They're related in that the acceleration tells us at a particular instant in time how much is the velocity increasing or decreasing. But other than that, they're independent quantities, so it should be the case that we could have something where the velocity is 0, but the acceleration is not. Here's one example of that. Let's say we throw something in the air. So if I throw something upwards in the air, on the way up, its velocity is upwards. So velocity is the easy one, right? You just look at what direction the object is traveling, that's the direction of its velocity. So the velocity is up, but on the way up, it's not picking up speed, it's slowing down. And that tells us that even though the velocity is upwards, the acceleration is downwards. So the acceleration would be, even for when it's going up, the velocity and the acceleration are in opposite directions. Now when something drops back down, that says that the velocity and the acceleration both are going to be in the downwards direction. So here's something you can use to try and determine what's going on. If something is picking up speed, if something is going faster and faster and faster, then the acceleration is in the same direction as the velocity. If it's slowing down, any object that's slowing down, the acceleration is opposite to the direction of the velocity. All right, so that's one way to try and keep track of this stuff. So I guess the question was saying, well, what about an object that's velocity is 0? And that would be right at the top. Notice that if you throw something up, it slows down. Momentarily, right at an instant at the top, its velocity goes to 0. But the acceleration never goes to 0. If the object were at rest and the acceleration were 0, the object would hover. It would just stay there. Now, the acceleration, we know that the acceleration is downwards the whole time because the velocity decreases, 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 becomes 0, but it doesn't stop at 0, it reverses and goes in the opposite direction. So it's kind of like this too. What if I walk over here, I'm slowing down, so my velocity is in the forward direction, my acceleration is back the other way, and then I slow down and momentarily stop, but then I start picking up speed in the other direction. Well, the velocity went to 0 at one point, but the acceleration was still back in the other direction. Okay, so something to keep track of. Let's see, part B says, if the acceleration is 0, does that mean that the velocity is 0? And no, the acceleration being 0 actually tells us that the velocity is constant. So let's think about this. How many different categories of motion are there? And there are a couple different categories. I've got these highlighted right here. And so one way to think about this is, okay, objects are either traveling at constant velocity or they are undergoing an acceleration. It's one or the other. It's got to be. It's got to be either an acceleration or they're moving at constant velocity. So now constant velocity would require having a fixed speed and a fixed direction. So constant velocity is only possible if you're going in straight line motion. If I go to the left or the right, I'm actually increasing my speed in a new direction. So constant velocity requires traveling in a straight line at a fixed direction with a fixed speed. And that means that the acceleration is 0. So we could divide up motion into two categories. We could say it's either constant velocity or it's accelerating. The object is undergoing an acceleration. Okay, so going back to this example where we threw something in the air, let's take a look at this. And so what we did was we threw something into the air from point A, and then it reached point B, momentarily stopped, and then it picked up speed and came back down. So the acceleration at point A, at point B, at point C, they were all downwards. And then the velocity was upwards on the way up. It momentarily became 0, and then it was downwards on the way down. Now, is there a way to graph this? Because graphing it might help explain what's going on. So the acceleration here is given as dv dt. And so let's throw the object into the air. And what's happening is when we throw it, at first it's got this really big velocity, but because of gravitational forces, that velocity steadily decreases. Now, here it is going from point A to point B, and notice when it gets to point B, it has stopped. So this represents a velocity of 0 on this plot. So here's where 0 velocity is, and point B is at 0. Now it doesn't stop there, it continues to come down. So when we look at the velocity as a function of time for something thrown up into the air and then it comes back down, this graph just has a straight line. The velocity just steadily decreases the whole time. The slope never changes, and that says that the acceleration is constant. All right. Now the acceleration for this is constant, and so I've graphed that also. And so the acceleration is a constant negative value. It's a constant downward acceleration. Okay. So we do want to get some examples here where we can show that velocities and accelerations, they don't have to be in the same direction. They don't have to have the same sign. One can go to 0 and the other one does not, and vice versa. So here's another example. Here is a car slowing down. So, and we're getting better and better at these diagrams. So here's the car. It's traveling 15 meters per second at a certain time, and we'll label that as 0 seconds. Now what it says is we're slowing down, so we're going to have to write that as an acceleration in the opposite direction. Since we've determined the velocity is in the positive direction, that would say that the acceleration on our coordinate system would be in the negative direction. So minus 2 meters per second squared. And then it says at time, at a later time, t2, of 5 seconds, what we find is that the velocity has slowed to 5 meters per second. Now I'm trying to think of, okay, so I wanted to highlight that we chose to have the car moving in the positive x direction. We chose that coordinate system. The driver puts on the brakes. What was the car's average acceleration? Okay, so these are the numbers that we have been given. Now they've kind of given us the answer on this one too, I guess. They're saying right here the acceleration is -2. Let's see if they got that right. So here's my diagram. This may be what your diagrams are going to look like. So, you know, when you're working the homework problems, draw diagrams. The midterms are going to ask you to, so you're guaranteed on the midterms that you're going to be asked to draw diagrams of what's going on. They're so important. So here's the car initially, and it's moving in that direction, and it's slowing down. Now that continues over a 5-second period where the car continues to move forward and continues to slow down. we can calculate an average acceleration as delta v over delta t. That's v2 minus v1, t2 minus t1. Now in this case, they did not give us the delta v and delta t directly, so we're going to make use of this formula and say we ended up at 5 meters per second. We started at 15. That's a difference of minus 10. So the velocity decreased by 10 meters per second. And that's during a time interval of 5 seconds. So yeah, I think they got the numbers right. It looks like it's minus 2.0 meters per second squared. And so what we have here is we have the velocity difference divided by the time interval. Okay, so this is an example of constant acceleration, and typically that's what we're going to work with for the most part. We will, you know, if there's a time when the accelerations are not constant, we'll have to point to that and remind ourselves that they're not constant in that particular example. But you can see in most of these examples, the accelerations are going to be considered to be constant. Now here is just pointing out there's a difference between negative acceleration and deceleration. Deceleration specifically says we're slowing down. Negative acceleration just means it's in a direction defined to be negative in a coordinate system that we've decided to use. Okay. So deceleration is slowing down, and you know, speeding up is speeding up. They're both considered to be accelerations. Deceleration's a subcategory. If I am slowing down, the acceleration and velocity are in opposite directions. If I'm speeding up, they're both in the same direction. So use those arrows to think about the problems. Okay, now I don't think we ever quite did this, so the slides, a little funny the order that they put them in. But the acceleration, the instantaneous, I guess that's it. So instantaneous acceleration is defined as the limit over shorter and shorter time intervals of dv divided by dt. So the graph now, just want to point out a few things here. We saw a graph very similar to this, talking about instantaneous velocity. With the velocity formula, this was x, and that was t, but now this is v, and that's t. So the graph now is v versus t. The graph we used before was x versus t, but it's kind of the same thing. It's a ratio of how much did the velocity increase? Well, it increased by a tiny amount over a tiny time interval. Now, what we can do is we can start putting some of these formulas together. What we can say is that the average velocity is given, if the acceleration is constant, then the average velocity would be taking the distance and dividing through by time. The acceleration would be given by v minus v naught divided by time. So this is assuming it's constant. So this is called average velocity, taking the distance divided by the time, and then the acceleration can be written in terms of the velocity. In addition, as the velocity is increasing at a constant rate, if it's constant acceleration, the average velocity then would be taking the starting velocity, v naught, the final velocity, v, and dividing that by 2. And so combining all those equations together, and I'm not so worried about doing the algebra behind this. So this is a formula for constant acceleration. It says that the position or the displacement of an object is determined by where it started plus whatever its starting velocity was times time, plus 1/2 times whatever acceleration it has, times t squared. And this formula works if the acceleration is a constant value. That's an important equation. We're going to be using that a lot. Okay, so putting all of these formulas together, what we end up with is this highlighted box of equations that we can use whenever there's constant acceleration. So that means when I read the problem and it either states, it explicitly states the acceleration is constant. In other examples, what it might do instead is kind of suggest that the acceleration can be considered to be constant. We'll see examples of those. But in any case, what we can do is go through and combining all of those equations that we just looked at, you can show that if the acceleration is constant, then the velocity is equal to whatever the velocity started out to be plus the accumulated effect of the acceleration. And that's given by a times t. So as time goes by, if the object continues to accelerate, its velocity will either steadily increase or it will steadily drop off, depending on the direction of the acceleration compared with the direction of the current velocity. So that gives us velocity as a function of time. Now the next equation is displacement as a function of time. And then finally this last one is it's the velocity as a function of displacements. Notice that this is in terms of time, this is in terms of time, but this one's not. This one we have used the other equations, we've combined them, eliminated the t, and come up with an equation that has v as a function of position. And so these three are very, very useful. Now, textbooks, our textbook in particular, has thrown in a fourth useful equation for constant acceleration, which I don't use very often. I'm going to say that does not show up nearly as often as the other three. The other three are going to be really vital. Okay, so in terms of problem solving then, so these kinematics problems, so we've introduced displacement, we've talked about velocities, specifically instantaneous velocity. So when we say the word velocity now, we just mean instantaneous. Same with acceleration. We looked at average accelerations, but then we looked at instantaneous accelerations, and now when we say acceleration, it means instantaneous. If we say average, then it refers to the average value. But if we drop the average statement, then we just mean instantaneous. So that's kind of the default. So let's see. It says read the whole problem, make sure you understand it, and then read it again. Now, that's really important. That's something I always have to remind myself to do because I've been doing physics for a good number of years now, and I've fallen into the habit of maybe not reading as carefully as I need to. I kind of skim to thinking I'm going to get all the important information, and it is better when I read more carefully. So make sure you guys, students kind of starting out with this, read the whole problem, make sure you understand it, write down all the information. So when I read a problem, start writing down all of the numbers that are given. If they give you a velocity, write it down. If they give you displacements, write those down. If they give you a time, write those down. Decide which objects are under study. If I've got an automobile, they're referring to an automobile and it's going at these speeds, well, it's not the pavement they're asking about, it's the automobile. So identify which objects are under study, find what the time intervals are, and draw diagrams. So draw a diagram, choose coordinate axes. Now it's conventional to say the positive direction is from left to right. Doesn't have to be. You'll see examples that we'll be doing very, very soon now. Up versus down. Now, more often than not, we use up as a positive direction and down as negative. But we'll see plenty of examples that we look at where we do the opposite. We say downwards is positive because it makes our formulas work more easily. So we have the freedom to be able to decide how to set up the coordinate systems and practicing deciding what's going to be the positive and negative direction. That's actually an important skill. So write down the given quantities. I think we mentioned that. And then write down maybe what we're trying to find out. what physics applies. So, and then at the bottom I've added in and highlighted, talk yourself through the setup. So I kind of constantly when I'm working physics problems, I'm talking myself through, and a lot of times it's just out loud, just hearing my own voice. I'm just talking to myself. So talk yourself through the setup. If you've got classmates that you can get together with and work on problems, talk to each other, think about what's going on. Listening to someone else talk through a problem is very useful. Listening to yourself talk through the problem is very useful. Make sure at the end of the day, if you are working together in groups, that you can go off on your own and still solve the problems. So, because that's what's going to be going on with the exams and the midterms. We do want each and every one of you individually to acquire those skills. Okay, so you want to be able to get to a point where you depend on yourself for solving all of these problems. If you happen to be doing a lot of your work in groups. Determine which equations are going to be most relevant, bring those out. Now, a lot of times students latch onto equations and they say, okay, as long as I have the equations, I'm going to pass this class. I'm going to do well because I'm going to get all the equations, I'm going to plug numbers into them. But the biggest part of physics is knowing which equations, which relationships apply. So an equation just represents a relationship between different physical quantities. Those equations we looked at showed how time, displacement, velocity, and accelerations are all related to each other. That's all they're doing. And so knowing how to adapt the equation to a particular problem, that's the important skill, right? And you should be able to look at an equation and go, oh yeah, this equation is telling me that the displacement is related to this velocity and this acceleration. And you should be able to kind of explain to yourself why the equation has the form that it does. Okay, so don't fall into that kind of trap of just thinking, oh, it's a bunch of symbols and I'm just going to plug numbers in and I'll be fine, because it doesn't work. It's not reliable. You need to understand what these equations are referring to. So practice that. Practice thinking about the equations. And then at the very end here, let's see, calculate the solutions, check the units, check that. Okay, this is already saying check that your result is sensible. Okay, it says that down here too. Anyway, this is all good. All these suggestions. This says calculate the solution, round it to the appropriate number of significant figures. So round back if needed, but make sure, I'm going to say, make sure you're always keeping 3 significant figures. Okay, always keep at least 3. I think if you get in that habit, I think you're going to do better rather than not as well. Look at the results, see if it's reasonable, see if it makes sense. Again, if you've got a car that's traveling 1,000,000 meters per second, there's likely a problem with that. And then go back and check units again. So keep track of checking all these things. I think that's a good time. We're probably at a good point where we could take a break. We're about halfway through the chapter. So let's go ahead and take a break right there. And then we'll come back and we will pick up. We'll look at some more examples in the later part of the chapter. If you guys have questions, stop by and we will take a look at the questions you got.